Hey, it's Mr. K doing a video for AP Physics 1 and C. Once again, still the classes are a bit aligned until we add in some not that hard calculus, but we'll get there. Um, Doing a video for an Atwoods machine, trying to update my videos that are on YouTube. Just to do the frame and frame kind of thing with me here. Just finished my coffee. If you've been watching along, just in sequential order. Then switching to water. It's a little bit late at night. And got the chickpeas still going. Gonna make some falafel. But yeah, let's cover this problem. So this is called an Atwoods machine, which is basically a pulley. Pulley's like a wheel. It's got some rope that goes up and around the pulley, and the rope is attached to two masses. And generally they are, bigger and smaller mass. And when usually we say that the pulley is like a super pulley, so there's no friction. You can definitely have friction up here if you wanted to. That would be more of a sea level problem, or a more advanced Physics 1 problem. And then while it's on the screen, this guy is super useful for drawing circles. It's a compass, but it's a different kind of compass. You might see the compasses that look like this. This is cooler, I think. I don't know. It depends on how you define cooler. If you're like steampunky, then the other one's cooler. But this one's more useful for me because then I can have the different circle settings with all these little dots. Anyway, so let's talk about this thing. This is one of the original ways that they used to determine what the acceleration due to gravity was, and it's kind of weird because nothing really falls at the rate of this, the rate of falling. But it's kind of cool that with forces, really in this problem, the thing that's causing everything to move in the first place is the force of gravity. And so we can use that to figure out the acceleration due to gravity if we were to do an experiment with it. So let's get started. Let's say that M1 is more massive than M2. And if that's the case, this thing's going to go like this. And then M1's going to go down, M2 is going to go up. And we'll solve it several ways. The first way is definitely going to be the more mathy way. But usually you guys are pretty set with the math. You've been trained up in the math for like a decade before you get to my class. And so we'll just start there, and then we'll start talking about the physics. So here we are. Always a good bet to draw a free body diagram for whatever objects are in your problem, in your system, really. And so, of course, here the system also includes the Earth, but we're not talking about energy. But anyways, so let's do a free body diagram. M1. We've got the force of gravity that goes down on M1. We're going to call that M1G. At the same time, we've got this force of gravity that goes down on M2, and I'm going to draw that a little bit shorter. That's going to be M2G, because if M1's more massive, we're going to do this. So there's that. And we have this rope that attaches both of them. So M1's going to go down. So there's going to be some amount of tension that points upwards. Now, we don't know how much tension that's going to be because we also haven't set what the masses are. I'm just going to call it T. But what I do know is that it's not going to be nearly as big as M1G because the thing still needs to go down, right? Still needs to accelerate down. With this other one, M2, I'm going to draw it going up as well, and we're going to call that tension, and we're actually going to call it the same tension. This tension over here on the left is the same tension on the right. It's the same rope. We're disregarding any kind of frictional forces with the pulley. The pulley will be massless as well, so no need to worry about tension being different. That is a big hint to say, yeah, in the future you might. But right now, let's not. So tension is going to go up over here on the right side, and it's going to be bigger than M2G because it needs to pull it up. It needs to be bigger. It needs to be a bigger force. So if we don't know much, we can at least do that, right? We can at least identify the forces that might be involved. There's no normal force. There's no surfaces interacting. We're good, okay? The next thing is going to be pretty important, though. We're going to define a direction of motion. And this direction of motion needs to be like positive and negative, and needs to apply to both objects the same way. So here's the issue. If we say up is positive, M1 goes down, M2 goes up. That displacement is the same, but we just said one is positive and one is negative. It needs to be the same sign. Okay? If we say, like, to the right is positive, nothing's moving to the right. That doesn't make any sense. So what we're going to say is that the direction of motion is this. It's going to be counterclockwise. And counterclockwise will be positive for us. Clockwise will be negative. Okay? And so what this does is anything that goes in the counterclockwise direction is positive. Anything that goes in the clockwise direction will be negative. And then that'll give us a consistent sign to apply to the math of this problem. And that'll help us out. So let's look at the sum of all forces for the left hand, the bigger block. And that's going to be sum, sigma, forces is equal to m1g minus tension. And the reason I'm putting m1g first in positive is because we just said that we're gonna consider counterclockwise to be our positive direction. Do you see how m1g is pointing in our counterclockwise direction? Tension is going the other way, so I'm going to assign a negative value to that. Okay. Don't forget that forces, being forces, they're always equal to ma. Sometimes a is 0. That's awesome if it is, but if it's not, then we got to work with it. We'll leave that there for now. Let's go over here. So again, counterclockwise is positive. I'm going to do sum of all forces, and we're going to have tension minus m2g for the same reason as what we just said before. And then it's equal to m2a. Notice how we use m1 and m2 based on which object we're talking about. This free body diagram, these forces apply to m1. These forces apply to m2. I hope I was on the screen that whole time. I'm not sure. We'll find out. Okay, so the goal here might be like, okay, Mr. K, give us some numbers. M1, let's make M1 like 10 kilograms, and we're going to make, really? We're going to make M2 like maybe 8 kilograms. And so you might say, Mr. K, give me some numbers. Okay, let's figure out what the acceleration is based off this. And you can totally do that. So M1 is going to be, Peeves is playing with her automatic ball thrower. M1 is going to be 10 kilograms. G is going to be 10. Not worried about that negative on the. Some of you are like, well, it's negative 10. It's okay. We've defined this direction as positive. Remember, minus tension. I don't know what that is. M1 again is 10, and then I've got A. So right now I've got 100 minus tension is equal to 10A. Over here, I've got tension is minus, M2 is going to be 8, G is still 10, and then it's negative now because it's in the clockwise direction, equals 8A. Okay, so we've got a system of equations kind of going on here. I really want the acceleration, so why don't let's just add. Let's just add. Some of you are like, but we can substitute. Yeah. Let's just add. So I'm gonna do this nicely for you. 100 minus t is equal to 10a. T minus 80 is equal to 8a. And so yeah, let's just add. So we can just add the right side. 10a plus 8a, that's going to be 18a. And then let's see, 100 minus 80, that's going to be 20. Negative t plus t, that's 0. And so we added. Yay. And then let's just divide by 18. So I've got 20 divided by 18 is equal to the acceleration, and that's meters per second squared. I didn't give myself enough room. Okay, so whatever this is, it's accelerating at a little bit more than 1 meter per second squared this way. And now that we know the acceleration, we can figure out speeds, or we can figure out distances given times and all that stuff. That is the mathy way to do it. It is. All right, it's mathy. If you really look at it, all we really did was add and subtract. A little bit of division, but it's just adding and subtracting forces. So let's do it in more of a physicsy way. And so put your physics cap on right now. Take your math cap off, because this is what the class is all about. So if I'm looking at this thing, what's trying to move everything? That's usually the question to ask if we're talking forces. And it's gravity, right? But gravity, the force of gravity is pulling M1 down, and it's also pulling M2 down at the same time. And they're fighting each other. And so whichever one has more force of gravity, that one wins. And that's the way that the system goes. It either rotates clockwise or counterclockwise. So let's just use that as a storytelling device. And so again, stick with me. Gravity is the thing that's moving everything. Force of gravity. How much force of gravity is there on M1? Well, Mr. K, that's mg. So we're just going to multiply the mass by 10. So there's 100 force of gravity newtons on M1. Let's keep that in our minds. What about M2? Well, that's 8 kilograms. So we'll just multiply that by 10. That's 80. So I've got 100 newtons fighting 80 newtons. Well, how much does M1 win by? That's like 20, right? And then the big question is, hey, what does F equal? And that's MA. So let's write down exactly what we just said. We just said that, hey, the force of gravity on M1, that was 100 newtons. We're going to take out 80 newtons because of M2. Those are fighting each other pretty directly. By doing this, we're ignoring all these internal forces that cancel out. Well, that gives us 20. And if these are forces, which they are, forces are equal to MA, aren't they? Now, the last question would be, what are these forces trying to move? And the answer is, well, everything, right? How much is everything? How much mass is everything? It's 10 kilograms and 8 kilograms. It's 18 kilograms. And so then we just move the 18 over and we're done. So the lesson that if you're still with me, I'm happy about that. First of all, if you're just skipping through, then you're missing everything. But the lesson here is that if you can identify the physics, the math comes out of it. It just does. Sometimes the numbers aren't nice, and you gotta be more mathy about it. But usually we'll try to use pretty easy numbers, so you can see the physics coming out of the problem, and that's the physics right there. Okay, so let's stop it here.